what we're going to do is we're going to have a look at using the wave equation, but we're going to be using it by making some conversions using some very common prefixes that we use. So I've put in a table here the different prefixes that you come across and the power of 10 that they indicate. So just a quick thing at this point, if you're not familiar with a notation like 10 to the minus 9, 10 to the minus 9 is effectively 1 divided by 10 to the power of 9. So it's like 0.0001 essentially. Okay, so we'll get to that a little bit later on. Let's first of all do some basics with the wave equation to make sure we know what we're doing with it. For the first thing, we want to rearrange to make frequency the subject. So it's in its normal form. The wave equation is speed is wavelength times frequency. So you can see at the moment frequency is multiplied by wavelength. So I'm going to divide both sides of the equation by wavelength to isolate the frequency, and that's the form we end up with. If you want to make wavelength the subject, instead we're going to divide both sides by the frequency, because that would leave wavelength by itself there. So those are kind of the three forms of the equation that we come across, either to calculate speed, to calculate frequency, or to calculate wavelength. There's another thing we can do is we can start thinking about time period as well. So we're going to get an equation to figure out what the time period of a wave is. So it says substitute in 1 over t for f. So let's do that first of all. So essentially what I'm going to do is I'm going to replace f with 1 over t, which is how we ended up with the expression that you can see. And to make t the subject, what I'm going to do is I'm going to multiply both sides of the equation by t and divide both sides by speed. I did those two steps at the same time, but those are the two steps I used, and we end up with an expression to calculate the time period of a wave. Okay. So now we're going to start integrating some conversions into this. So we've got microwaves and the type of electromagnetic radiation with a frequency of 2 gigahertz. That actually sounds pretty high for a microwave, if I'm honest, but doesn't matter for the purposes of these questions. So in terms of this, so first of all, microwave is in the electromagnetic spectrum, which means it travels at 3 times 10 to the 8th. So we know what the speed is, because it's an electromagnetic wave, and we know the frequency. So we want the form of the equation to calculate wavelength, and we can see, if you look at the frequency in here, we can see I've put in 2 times 10 to the 9, because you can see it says 2 gigahertz in the question, and giga means 10 to the power of 9. We plug those numbers into the equation. So when we're dealing with standard form and we're doing division, what you do is you do the numbers in front, the mantissas, you divide those, so that's why we end up with 1.5, and then you find the difference between the top and the bottom line. So you can see the difference is -1, so that, and then we can change that to the normal form that we get 0.15 meters. Okay, we want to convert our answer into millimeters. So the first thing I think about is, well, a millimeter is a shorter unit of distance. So if we're converting a distance in meters into millimeters, we should get a bigger number, because a millimeter is much smaller than a meter. And more specifically, there are 1,000 millimeters, or 10 to the 3 millimeters in 1 meter. So it's going to get bigger by a factor of 1,000 to give us 150 millimeters. If in terms of converting our answer into kilometers, now a kilometer is a much bigger unit of distance. So when we go from meters into kilometers, I'd expect the number to get smaller, because a kilometer is much bigger. So you should know a kilometer is 1,000 meters, which means a meter is 10 to the -3, or 1 over 10 to the 3 kilometers. And so once we know that, we can multiply our distance in meters by that conversion factor, 10 to the -3, and we end up with a distance in kilometers. Alrighty, let's have another scenario. So we've got X-rays, another type of electromagnetic wave. They're traveling in a vacuum, and they have a wavelength of 0.5 nanometers. We want to know the frequency. So again, electromagnetic wave in a vacuum, speed is 3 times 10 to the 8. And the wavelength, that's nanometers, so that's times 10 to the -9. Nano is a really tiny unit of distance. So there we get our wavelength and our speed. Then we can plug those into our equation, and we end up with doing 3 divided by 5 gives us 0.6. 10 to the 8 divided by 10 to the minus 10, you end up with 10 to the 18, because it's 8 minus 10. And then once we actually turn that into an appropriate standard form, that's going to be 6 times 10 to the 17 hertz. Convert it into gigahertz. Well, a gigahertz is a really big unit of frequency. It's a billion hertz. And we can see that 10 to the 17 is going to be 10 to the 8 times 10 to the 9, which gives us 10 to the 17. So you can see the frequency is just going to be 6 times 10 to the 8 gigahertz. So it's still a large quantity of those. So in digital storage, a petabyte is 10 to the 15 bytes. Calculate the frequency in petahertz. Okay, so this is one that wasn't given at the start, but we've been given enough information to figure it out. So a petahertz is a 10 to the 15, so it's a really big unit of frequency, bigger even than a gigahertz. We can apply the same way we did to the previous question to figure out how many we need, and then we're just going to do 6 times 10 to the 2 petahertz, or 600 petahertz. Okay, so then just thinking about some general cases in terms of going back to the refraction topic. So the X-ray goes from a vacuum into water. Describe how the properties of the wave would change. So vacuum has a very, very low refractive index. Well, it has a refractive index of 1, and water has a refractive index higher than that, and that means that speed would decrease. So water is a more dense medium, so we're going to decrease the speed. Frequency never changes. So once a wave has left the source that emits it, its frequency cannot change. Okay, so that's going to stay constant, which is nice. And then in terms of the wavelength, we're going to see it decrease. So if you think about the wave equation, if frequency is constant, wavelength and speed are directly proportional to each other. So if speed decreases, the wavelength has to decrease as well. And if you look at it on a wavefront diagram, you actually see that happening. Okay, so a challenging question to finish off, just to see how you can think. So we've got a person standing on a mountain on a foggy day, which means they can see a total distance of 500 meters. A fighter jet is traveling on a horizontal flight path at the same altitude as the person on the mountain. A person uses a stopwatch to measure the time from the jet first appearing and when the sound is loudest, and that's 1.6 seconds. And they measure the time being between the sound being loudest and the jet disappearing, which is 1 second. Find the shortest distance between the jet and the person using the speed of sound is 340 meters per second. And you can assume light takes no time to travel from the jet to the person. And this is a very common assumption we make in physics. Over a distance of 500 meters, light travels at 3 times 10 to the 8 meters per second. So it takes basically 0 time to travel, which is why we're going to assume that. Okay, so the first thing I'm going to try and do to solve this is actually draw a diagram of what that looks like. So I'm standing on the left at the intersection of those 2 arrows, and the bottom is where the jet first appears in our vision, which we know is 500 meters away from us. And at the top is where the jet leaves our vision, which again we know is 500 meters. And we're told the jet is traveling in a straight line at constant speed, so we've effectively formed a giant triangle there. So the thing to realize here is when the jet sounds the loudest, it will have gone past its closest point because it takes some time for the sound to travel from the jet and its closest point to us. So that's why we've got the 1.6 seconds, because it's gone slightly past the midpoint by the time you hear it. And then that's why we get the slightly different times. So the first thing I'm going to do is I'm going to figure out how long it takes to actually get to the closest position. So it's completely symmetrical. So you can see that it's going to take 1.3 seconds to get to the midpoint, because it takes 2.6 seconds to do the whole side of the triangle. So it must be 1.3 to do the middle section of the triangle. And then we can figure out, well, we actually heard the jet loudest at 1.6 seconds. So we know it's taken 0.3 seconds for the sound to travel from the closest position to you. Then we can just use the speed equals distance over time equation. We want distance, so we're going to do distance is speed times time. We know the speed because we were told in the question it's 340. We know the time, and we get a distance of 102 meters, or we should probably give this to two significant figures, so it would be actually 100 meters to two significant figures. And that finishes off this set of questions.